inglés presentando al ponente. Este es el último seminario de la serie de este año de Física y Cómputo. Y pues en esta ocasión para nosotros es un seminario extraordinario porque nos invitamos a un colega que ya ha trabajado, hemos colaborado con él, ¿no? De la Universidad de Marsella, que va a hablar sobre singularidades temporales, ¿no? Hablar inglés, para presentarlo. For me, I am glad to present Patrice Le Gal, who works in Marseille. He will speak about the finite time singularities waves. No?
Okay, thank you, Gerardo. Is me to speak?
Yes.
Yeah. Okay. So thank you to host me. I would say once again here. Okay. I recognize your faces, guys, and I'm happy to be here. Working in the fluid mechanics labs and also giving this seminar. So I'm sorry, last year I promised I should learn Spanish. I didn't. Okay, I don't know. And you know why? Because I spend my time playing with things. So you hear, this is a ping pong ball, okay? Okay, so you hear this frequency increasing in time. Okay, once again. Okay, in fact, if you do the analysis, and we can do it now here, you will see that the frequency will diverge in a finite time. Okay, so to do that, we will neglect, you know, if the ball can be deformed, and we just said that there is a certain amount of energy that will go away with sound, with deformations, with heat. And so after the first bounce, the velocity at bounce number n plus 1 is epsilon times the velocity vn, okay? With epsilon less than 1, because we know that the next bounce will be less than the first one, okay? So if we call T0 the first time for the first bounce, T1, T2, and so on, it's very easy, you can imagine, to calculate the T and xn, okay? And in fact, all the calculations are done in this paper, and also some analysis on experiments in the group of Stefan Fauve, and that was a paper in '98, okay? That's an old paper. And so what you write down is just that the acceleration is equal to the minus equal the weight, okay? You integrate the equation, you put the boundary conditions, and you find the Tn, okay? And the Tn, you can write it under this shape, h is naught divided by the gravity, and so epsilon to the power n, and you can sum all these Tn to find what will be the limit, okay? What is the limit when the ball will stop? And you find when you add all this stuff, of course you have a series here, which is a geometric series, and the formula is, we know that the sum of a series is 1 plus epsilon, 1 minus epsilon here, times this parameter here, okay? So after a finite time, okay, the ball will stop and the frequency will go to infinity. In fact, you can do a little bit more. If you said that, so these were the delta t, if you want, between these bonds and these bonds, but you can calculate also this time here, this instant, and we call that this instant psi n. So psi n will be simply the sum of the ti. Okay, and you know what is the period of the bounce? So the period of a bounce is simply the derivative of Cn versus n. So the frequency is the inverse. Okay, so the frequency is dn divided by the time Cn, and when you make the derivative of that, you find that the frequency diverges as 1 over psi n minus this tau infinity there. Okay, so if we record this frequency and we plot it versus time, you see that this thing will go to infinity like that. So this is what is called a finite time singularity. Okay? And I like that much because you see the present, imagine we are here, the present is driven by the existence of this finite time singularity, yes? So if we are now, we try to record the frequency. Oh, the finite time singularity in the future does not exist because I stopped the ball. But it has an influence on the present time because the frequency was moving along this one over time things, okay? So this is very strange, yes? What we are living now, when there is a finite time singularity, this thing will drive the present even if it does not exist. Okay? I think this is quite neat. So this is a very, you see, easy example to understand. And there is also what is called the Newton disk. Maybe you heard about that. It's a flat disk, and it's like a coin. Okay, when you throw a coin on the table, you see the coin will wobble like that. Same thing. Okay, you can write down the equations, and you can find these finite time singularities too. And there is also another, which is very well known finite time singularity. So this is the experiment. You remember some years ago, there was the discovery of gravitational waves because of the coalescence of two black holes. Okay, so this is the LIGO and Virgo experiment. So they have this kind of detectors, okay, with 4 kilometers arms, and they wanted to know if the space-time is really deformed by the matter. Okay, so you need a big amount of matter that is moving somewhere, and that exists when you have two black holes somewhere in the universe. And this thing, in fact, will get close together, will turn one around the other one, and you can imagine these two intense mass rotating one around the other one like that, and this will deform the space-time. And Einstein predicted the existence of the gravitational waves, okay? And this thing will coalesce one against the other one, okay? And this is a numerical calculation. These were not black holes, but they were neutron stars, big stars, very heavy stars, okay? And you see the signal that this researcher in astrophysics, Blanchet, he's French, he calculated. So you have these two stars arriving one around the other one. They rotate faster and faster and faster, and this is the signal here, and there they coalesce, okay? And if we do the calculations, and you will see that it is not because it is a gravitational relativity that it is that, to some extent, that difficult, okay? And I can explain that to you now. So you have the two stars or the two black holes here, M1 and M2. They are separated by the distance a, and there is the barycenter, okay, the center of mass of these two stars somewhere on the line there, and the radius of rotation of the first one versus the center of mass is a1, and the same for the other side, it is a2. We will need this notation, okay, and these are classical notation in astrophysics, the reduced mass mu and the sum of the two mass m, and there is also this combination of these two under this m there, Gothic m there. So the first thing to remember from high school or beginning first year at the university is the Kepler law, okay? And the Kepler law, we say the t square will be proportional to the cubic power of the radius, okay? So this is one law to remember. Second law we have to remember is what is the total energy. Total energy is the kinetic energy. It is here for the star number 1, star number 2, and the potential energy here because the minus sign, because the things can lose energy when they fall one onto the other. And if you add another equation, which is the momentum equation for each star, you say that the centrifugal force is equal to the weight, if you want, to the attractive force. You can reduce this thing to this term, minus 1/2 g mu m divided by the radius a, okay? Now, we can derive that in time. We say there is a loss of energy, so what is d over dt? So So we derive this thing, and because we have a to the power minus 1 here, we have something which is d over dt, the minus will disappear, is equal to that, okay? G mu m 2a squared dA over dt, okay? And this is where Einstein came into play, okay, with a very big calculation to do, and Einstein was able to calculate what is the damping of this energy because of a loss of energy because of a gravitational wave. And after you replace that with Einstein formula, and you calculate the change of radius, okay? So the change of radius is dA over dt is equal to this thing here, okay? So we see that if we integrate that, a cubed dA will give a4 dt this side. So you see that a will go like time at the power 1/4. And in fact, what can be shown is that the energy of the waves, the gravitational waves, is in 1 over a, 1 over the distance between the two stars. So that will give an energy, if you want not an energy, an amplitude in time, sorry, there is a parenthesis here missing, to the power minus 1/4. Okay? Now what you can do also is you take the Kepler formula and you know, okay, t squared goes like a cubed, so t goes like a to the power 3/2. So if we calculate the frequency and you can replace the a and so on, everything, and you calculate the frequency as a function of time, and we find the power minus 3/8. Okay? So when you have these two colliding objects in the sky, the amplitude of the gravitational wave, time to the power minus 1/4, and frequency to the power minus 3/8. So this is a simulation of this signal there, here. There is a finite time, it is when the two objects collide, okay? And so this is what you can calculate, and this is what they detected, okay? So that was detected, and the reference of the Fish Revelator paper is not here, but I can give it to you. So this is the LIGO, try to get the photo again. Okay, and so this is the frequency as a function of time, and you see this thing there, this thing there is a minus 3/8, in fact, that we calculated before, okay? So they were able to find this signal because the signals, the raw signal is very noisy. You can imagine. Okay, they are measuring crazy thing, 10 to the power. The accuracy is crazy. But they know the advantage. They know what is the shape of a signal. Okay, so when you know the shape of something, you try to find in the noise. This is much more easy to get. Okay, so this is the reason of their success. Okay. Okay, so these are two examples, one from common life and one from the universe, okay? So now maybe we can be back to fluid mechanics. And in fluid mechanics also we have finite time singularities. In fact, in fluids there are two types of finite time singularities. One finite time singularities are bulk singularities, and the demonstration is not done, but this is one of his famous theorems that if you demonstrate it, you will win $1 million, okay? It's a $1 million theorem. If you can prove that if you start from smooth initial conditions for the Navier-Stokes equation, and you can prove that in a finite time, you have a singular behavior of the velocity field, okay? So these I would say hard singularities. We don't know if they exist, okay? But maybe they exist, or maybe this is the reason why we have intermittency in turbulence, okay? So these things are still to be demonstrated, and people are really active on this subject of turbulence, trying to find finite time singularities in the field. There are, I would say, weak singularities or most obvious singularities on free surface, on free surfaces like water or water surface like that. And one of the easiest model of water surface, I would say, is the 1D Burger's equation. Okay, so the 1D Burger's equation is just the convection equation, and you can add here if you want a viscous term, okay, nu Laplacian of u, okay, that will mimic a viscous term, a viscosity. But here I said, okay, I don't want to take any viscous behavior, okay, so in fact I will compute this equation starting from a solution nu at time t equals 0, which is quite smooth, and I will let it go to see what happens. And we know the result of that, okay? If we compute that, you start with a Gaussian shape, just as an initial condition. This is the u, and you do that. This is a MATLAB program, okay? That's very easy, Euler integration of this equation. And you will see what? You will see that there is a front which is created on the Berger equation, okay? So the slope here is getting to go to infinity in a finite time, okay? So this is what I wrote here. So on this Berger equation, there is a finite time singularity too, okay? Which is on this shape. So what I will do now is to try to know what is the shape of the singular behavior of the wave there. And in fact, this is exactly the same type of singular behavior you have on a wave when you are on a very shallow water wave. When you are nearby the beach, okay, where you have shallow water, so you have the shallow water equations, which are a little bit more complicated than that, but we can mimic these shallow water equations by the Berger's equation. And what we see is that we know that the dispersion relation of shallow water waves is a function of h, okay? The velocity is square root of gh, okay? Square root of gh, h the height of water. So if you have these waves, the top of the waves see a depth which is larger than the trough, okay? So in fact, the top of the wave will go faster than the bottom of the wave there, just because the amplitude is there, okay? And this is a kind of nonlinear behavior of the wave, okay? So this is the reason why we have these finite time singularities in these waves. And so what I am going to do is to redemonstrate what Poisson did in 1808. You know, this is not a very recent demonstration. But you recognize here a space-time diagram of a movie that I did before. So here you have a u as a function of x at different time along here. So you have a smooth bump, okay? The front is forming here. Oh, here is the first time where I see the singularity. Okay, this is the vertical slope of a wave. Okay, after I will have this singular behavior will extend, and I have 2 points where I have a vertical slope. Okay, one is in the front, one is in the back of a wave. Okay, so this I join all these points with this red line there. Okay, if I see this red line from the side, this is the green curve. So the green curve is here. Okay, it's a parabola. Okay, so here it has a vertical slope, du divided by dt is equal to infinity here. Okay, and if you look at this curve from the top, it has this kind of singular behavior like that. It's like a corner. Okay, it's a cusp. Okay, that we have like that. So you see, it's a curve which, imagine I have a rope here. Here it's a parabolic behavior, and after I twist it, and I look at it like that, okay? So it will be like that in one direction, smooth in the other direction, okay? So this is, and what I want to do is, I want to know what is the shape of this, of the blue line, of the blue curve, versus the singular behavior here. So what Poisson did, in fact, he said, okay, I want to find a solution which I can write under the solution, under the form u equal x of time, will be a solution u0 that will be transported, okay? That is u0 of x minus ut. After you said, okay, I will inverse this thing, saying that the function f is the inverse of u naught. So I have f of u is equal to x minus ut. Okay? So what I want to find is an approximation of the function f. And what we can do now is we take the derivative of f versus u. So you say df over du is equal to what? Dx over du. But I know that dx over du is equal to 0 because du over dx is equal to infinity. Okay? So this first term can disappear. And after I have the ut. So I take the derivative of that versus u, and I find that it is t. Okay? So I have this relation. Now I take a second time the derivative in u of this formula. And I said dt over du is equal to 0. The first term will disappear, always because of the same trick, because du over dt is equal to 0. And I find that the second derivative of f versus u is equal to 0. Okay? So the only way, in fact, to find a formula for f, Taylor, if you want a Taylor expansion, is to say that f starts with a u cube. Okay? It cannot have a u square, and it may have a u, but the u is multiplied by t. We saw that. And in fact, we keep only the u cube term. So if I said before that f is equal to x minus ut, I know that u cube plus x minus ut is the first term in the Taylor development of the thing, expansion. Okay? So what do we learn with this formula? That x has the same weight as ut, okay, which has the same weight as u cube. Okay? So in fact, if I said u cube is equivalent to ut, that will give u square equivalent to t, so u has to behave like t to the power 1/2. Okay? X now is to the power 3/2 of time, so x is u cube, so x is u cube, so 3/2, x is 3/2 of time. Okay? So you find the singular behavior, and that means that in fact if we calculate the slope du over dx, it will vary as 1 over t at a final time singularity. But this final time singularity, I didn't say, but my point here, I said that was time t equals 0. Okay? So the t infinity was in fact 0 in this case. Okay? So the singular behavior is like that on this equation. In fact, all these singular behaviors can be interpreted by algebraic shapes of different objects. And that was in fact organized and classified by René Thom in the 60s, 70s, who wrote a theory which he called the theory of the catastrophes, and he classifies this thing. So the first catastrophe we can meet is when you take z as a function of a and b, two variables like that, and you say, I want z squared minus b equals 0. Okay? And this is called the fold, in fact. Okay? So this is a drawing of a fold. Okay? So you can imagine that if you are on this b line and you walk on this fold, it's like a tissue that you fold, okay? You walk on it, and at one moment you can fall down, okay? So this is the classical thing. The second catastrophe, and these nice drawings are in French, the explanation are in French because this is from a French person who wrote this popular article on the catastrophe in this French journal. But I like the drawing, so I put it here. So the second catastrophe is the cusp. So la France is the cusp. I don't know what is the Spanish name of that. Someone knows maybe? You know when we have pullovers like that, sometimes we have this kind of fold. Locally it is folded, but after it is relaxed. I don't know how you call that. You don't know? In what? Liero? Okay, so this is in English, at least it is the cusp, and in French it is la France. Okay, and you have over like that with different name here. You have la queue d'aronde in English is the sparrow tail, something like that, and a different kind of shapes like that you can classify. And if you remember my drawing of a space-time drawing like that, in fact, I have exactly that, okay? I have exactly a cusp, and I can even go there, but if I say that time t is this direction, space x is this direction, z is the height of the water, you see that the wave is flat here, a little bam, smooth, and bing, singular behavior here, okay? And on each side of this side, on this side, here, I have two folds. These are called acoustics, in fact, okay? So we recover by the demonstration done by Poisson in 1808, in fact, we recover this shape, which is nothing more than this shape, which is hidden under the behavior of a wave, like that. With Yves Pommeau, his name is not written on this one, Yves Pommeau is a French theoretician. He had one question one day, and this question was, okay, there is this singular behavior of the Berger equation of a wave there. okay, but this is 1D, okay. What happened on the second direction there? So you see the wave will break at one point. What is the behavior along the crest of the wave? And we may, after a quite long demonstration, it's possible to prove that the unfolding, this is a way that people call that, the unfolding of a singularity, which is this equation there that we saw, in fact should be completed by a term which is, the time is transformed in t minus y squared, okay? And we see the scaling here is in fact that y behaves like the square root of time. So in fact, the singular behavior there will expand and will propagate, if you want, on the crest of the wave as the square root of time, like that. And if we simulate this equation, and simulating this equation and putting a point, if you want, I will start it, a point where the behavior is singular, we see that, okay? So I call that the surfer equation because you need to think you are surfing the wave and you look the point where the slope is vertical, where there is a singular point, okay? So this is, I come back again. So we will see the, you see we are on the crest of the wave, following the wave, and you see that it breaks like that, okay? And you see, so I do experiments and I say, wow, living in Marseille, nearby the seaside of the Mediterranean Sea, it would be crazy not to try to see if this is true or not, yeah? So we did the experiment, but we didn't do that on the sea, okay? We went on the lab, we had a water table with 2 or 3 centimeters of water. We had a wave maker at one side of a table, and we make a small wave, big like that, and the wave will break at one point. We have a fast video camera, and we can follow what's going on. Okay, so this is a movie here, and you see that here, you see there is a little tank here, but we'll see a little bit better after. Because of the light, we see also its traces here. You see it there? Okay, so you see this thing will propagate like that, and in fact, it has indeed a square root behavior, and we can do even better. It was a student, forgot his first name. I forgot his first name, sorry, and who made this experiment on the movie, and you will see, so that we have a superimposition of a theory with expansion in time and along x, and the expansion in time along y. So at time t equals 0, we fit, you see we have a free parameter which is the, if you want the scaling, okay, what is 1 centimeter, okay, in true life we know what it is. So we fit the starting curve at time t equals 0, and after we let it go, okay, and you will see what's going on. You see the blue line completely follow and expand in this direction and in this direction the same way as the wave. You may notice that the wave is a bit beyond. The wave is a bit behind, the true wave is a bit behind because it lost energy because of its capillarity behavior there. So some energy is lost, okay? So we do not really exactly fit the prediction because of these waves which are not in the theory. Okay, why not? So we are thinking of these waves, which are 2D surface waves, so 1D first, 2D after that. Can we have singular behavior or this kind of front on 3D waves? So in fluid mechanics, the 3D waves we have is sound, okay? So what is the singular behavior of sound? It is, so you have a sound wave, and the front will be sharp. And this is a shock, in fact, okay? So I said, is it possible that, imagine you start a shock, I don't know, you have a gun, you shot a bullet there, the bullet is getting out of the gun, so you have a shock there expanding. I would like to measure this expansion. Is it also a square root of time for the singular behavior of a shock? Okay, and of course not easy to do the experiment, but I went on Google and I said, okay, is there a movie of sonic boom that we can find on Google, okay? And there are some beautiful movies, and this is one there. You will see, I will play it several times. So this is a fighter, okay? A fighter which has been recorded and is flying just above the sea. And because it is just above the sea, air is full of water vapor. And when the shock is formed, there is change of pressure, and vapor condensates in a cloud to make little droplets. Okay, so I ask myself, imagine I measure the size of a cloud, maybe what will be the law of expansion? Maybe it will follow the expansion of a shock. So it is what I did here. Okay, so we see the movie again. Okay, and you see there will be the cloud phase one blow up. You see it started a little bit above there and expand. And I had 1, 2, 3, 4, 5, 6 or 7 images showing this cloud, and I measured that 5 times. Okay, so these are the 5 measurements on the different images that I had. And you see this is not bad. This is the square root of time. Okay. So it seems that it applies also on shock waves, this stuff. So I think they are very, very universal behavior, and this is sustained. In fact, these behaviors are sustained because of this catastrophe shapes. You know, all these shapes, the cusp, the fold, and all these other catastrophe things. Okay, now we can ask ourselves. So after sound, can we have a final time singular behavior with light? And this is very common stuff. With light, it is just if you take a glass and you focus light on it here, okay, and you see that there will be a singular behavior because the intensity of light will be concentrated there at the focus point, okay. And here is the same. So imagine here we have a parabolic mirror. So here it's a mirror. In fact, you will see later, what I need to have an emitter. So imagine I have an emitter of light here on the blue parabolic behavior, and I will send a wave. So first there is a ray like that, and you can easily imagine that there is a region of space where you have 3 rays arriving together, and another region of space, in fact, where there is only 1 ray. Okay, and the separation between these 2 behaviors, you can very easily find the formula, is called the Huygens cusp, and it has this shape there. So again, the cusp is there, okay? And this is the complete theory of a thing, okay? You can have a parabolic behavior, you send rays, and you can calculate also the phase of the waves, and you can calculate what is called the ray theory, and all the rays emitted by the parabola will focus on this point, and you have this behavior will be given, this is the 8 of the amplitude of a wave, and will be given by the square root of this thing, where d is the distance, okay, of the position of a cusp here. Okay, so this is very well known in optics. In fact, it is not totally true. It's not totally true because these waves, when they are very near the singular behavior, with the singular behavior will be at a scale which is not far from the wavelength of a light. Okay? And in fact, this ray theory or geometrical optic theory has been corrected by what is called the diffraction theory. So instead of speaking of rays, we speak about we have to integrate, if you want, the waves on all the different directions that they have. Okay, so this is the square root of d that we had before. Okay, coming just from the conservation of energy, but we have to take into account this cosine, which is the angle of the rays compared to the direction we are looking at, and here it's just the sinusoidal function. And what Percy did in 1946, he made the Taylor expansion of his d here around the singular behavior, around the cusp, and so this is the expansion, and we can rewrite this equation, the eta there, which is the intensity of light, we can rewrite it under this form there. And what is magic, but not magic, is here in the phase, we recover something with new parameters, okay, which is, you recognize the S4, US square, Vs, and this is in fact the fold, sorry, not the fold, the cusp, which is hidden there under this formula, okay. And so having learned this stuff, we came back to fluid mechanics, and that was done with Gerardo, and that was done first in Marseille during your sabbatical stay some years ago, and after Gerardo set up a nice experiment on water waves, trying to do the same, okay? So the question is, can we focus surface waves the same way we are focusing light, okay, with a lens, okay? So to do that, we have a parabolic wave maker, which is here. Maybe we see a little bit here, and we create waves, and we see that in the lab, we see that the waves will focus and will even break at the focus point, okay? So we wrote the first papers that was already 5 years ago, and we just last year published a paper on new results, on new experiments, and I will show here a little bit of the results for small amplitude waves, okay, where indeed we recover, these are the experiments, okay, the color are really the experiment that Gerardo did in his lab, okay, so these are the waves propagating. In white here we have the theory, and you see that the waves collapse there and focuses right on the theory. And what we wanted to do is, can we compare the per se theory to the measurement in the lab, okay? So the per se theory, I recall you, takes into account the diffraction, okay? And you see that the dotted lines here is the per se integral here, and you see that we recover perfectly the results, okay? Look at this one. The integral, the per se integral will do exactly the good behavior. The geometric theory of light will give the blue lines there. You see with a divergence here, but we expect if we have no diffractions. Okay, so that was done in the lab, and working on that, and that will be my last part of my talk. Working on that, I create a piece of art with a collaboration with an artist, and I would like to share this thing with you. So we redid the same experiment, and so this is in fact the table, water table. We have water in it, and here we have a parabolic wave maker here, and we have a motor, okay, to excite the wave. And what we did is we recorded this movie at a high speed also, with a fast camera. And when the artist saw this movie, she said, wow, we should present this movie in an exhibition, okay? So we decided to present this movie on an exhibition to explain to people what is a wave breaking. There was all this work on the singular behavior of waves. And also, maybe I can come back to the movie to explain something. Up here. So we discovered also something which I cannot yet explain. You see these capillary waves, this I will see you. This one, you see them? They are fixed in the laboratory frame. You see that? They do not propagate. Okay? So this is very strange. It seems that we have capillary waves. They are on the top of the gravity waves, but they are fixed in the lab. So certainly there is a kind of resonance with the phase velocity should be back, but they are transported by the water that breaks. Okay, the wave should break. So it's a kind of composition of the phase velocity. But I have no theoretical explanation of that, and I talk to people, specialists of waves and wave breaking, and they do not know why we observe that. And this is the exhibition that we installed in Marseille, and also in different other places, in Paris also once. So we had 6 photographies like that on maybe 50 by 50, half a meter by half a meter. They were mounted on a closed box with light coming from inside, and it was a black and white photography. You recognize here the waves and the capillary waves. And I was very admirative, is correct to say that, of the work of the artist. She was in the lab working with me, and she noticed that everything was transparent, okay? Everything was a kind of transparent greenish, because the table is glass, is a bit greenish, okay? The water is transparent. And she said, wow, we have to try to communicate this feeling to the public. And the idea she had is not to have a screen like this one, okay? This normal screen that all of us scientists we will have done to present a movie. What she did is she took 4 plates of glass plates, maybe 2 meter high, 120 meter width, like that were fixed on the ceiling like that. 4 of them, distant half a meter, and each glass plate is covered by a kind of tissue, very light tissue, to make a semi-transparent screen. So in fact, the video is projected here, but the video is stopped on the first screen by a certain amount of light. You see the wave, but on the second screen you have also the wave that continue, of course, the movie continues through the different screens. So it's a bit like you can turn around the screen, okay? You turn around them and you can see the waves in volume, in fact, okay? So that was a very neat and very good idea and a very big success for this presentation. Okay, myself, I was, after this work with her, we were invited in California to discuss and to create pieces with other artists. And can you guess what is, do you understand what is this piece of art? This is a sculpture that I created, okay? So in fact, this is exactly the unfolding of the cusp. Do you remember this parabolic shape there? And we have the X-rays that goes, and they have this angular behavior on the cusp, like that. So now you take this ray of light, for instance, and the second one, you put it a little bit above, on like that, okay? And this is how I created this sculpture, what I call the cusp, of course, okay? Okay, and this collaboration with the artist took different form, okay? This is a piece, I will start with this one. This is a big piece of art, okay? 6 meter long, maybe 1 meter and a half height, like that. And these metallic blades are very thin, maybe 100 microns. And they are driven, each of them, by something like 30 or something like that, 30-something motors. Altogether, we have 147, I remember, motors, small motors. And these motors are connected, they are microcomputers, connected to buoys in different parts of the world. Okay? So this piece of metal is connected to the waves which are recorded in, so one was in Hawaii, the other one was in maybe not far from Mexico, another one was in the Atlantic, North Atlantic, South Atlantic, and also nearby Japan. Okay, so we have everywhere. I know it was not. Yeah, it was around the Pacific. I remember now. So all around the Pacific, we get the data from internet. You can. It's not easy to do, but we can do it. Okay, we get the data. It's not real time. The data are refreshed every 2 hours, and they send the spectra. So you know the spectra of the sea every 2 hours somewhere in the world. So after you get the spectra, you make an inverse Fourier transform of it. We don't know the phase, so I put a random phase on the system. So you can play the waves in the Atlantic Ocean in real time. Okay, so you are in France, in Marseille, or in Paris, or in Mexico if you invite me to present the piece, and you can really have a feeling that the world is a small world. Okay, and we can have a feeling what are the waves in different places of the world. And we had a small piece, this one is smaller, and it's called Honolulu, because it is connected to the buoy in Honolulu, okay? And this one is maybe 1 meter, this is for, you can go on vacation with it, okay, with this one. Okay, this was another piece of art. It was an invitation we have in Deauville. Maybe you heard about Deauville, it's a city in Normandy. And the goal was to create fountains for cities. Okay, and this is, so that's what I can play it again. This is my idea of fountain was to create a solitary wave in a circular tunnel, like the circular tank, like that, and you see that you do not see how the wave is, how the energy is injected there, okay? And in fact, so this, coming back to the public, the sensation we want to give to the public, that time is a cyclic thing, okay? It has no beginning, no end, okay? And I promise when people, they saw these waves, you stay there for, I won't say hours, but for a long time to try to see the solitary wave running around like that, okay? Like a clock somehow. And just to finish with, we can do art, but we can also come back to physics, okay? So this is always, art science is always an interplay between science and art, okay? So I presented some pieces of art, and we can come back on the solitary waves also. And the reason is that one day I came into a museum where the piece was presented, and I asked the person in charge of running the museum if it was okay, and the lady said, oh yes, perfect, good. I arrived in the room where the solitary wave was supposed to run, no run at the surface, no wave at the surface, okay? Of course, she has switched on all the buttons and everything, but no wave. I said, wow, what's going on? My wave has disappeared, you know? And so I tried to understand what is this strange behavior. And what we did, and you come back to the equation of motion of a solitary waves, which are the KdV equation that we may know. And this is this is in fact the shape of a solitary wave there. And you can simulate the KdV equation with a periodic forcing, because I would like to go there. The way I inject energy is by a little, very little pipe under, you see this is a cross-section of the channel there. And there is a little pipe, and there is maybe big like that, 5 centimeters. It is in stainless steel. And every period, I inject a jet which is pulsed, okay? And I can calculate the time the solitary wave needs to make a complete turn. So I can synchronize the injection of energy, okay? So every time the wave is arriving, I will give it a little bit of energy every time, okay? And it's very difficult to see that because it is underwater, okay? So you don't see the jet, okay? So coming back to this equation, you see that if you are not in a resonant forcing, for instance this one, or if you do nothing first, if you do nothing, you see that the solitary wave will propagate 1 turn, 2 turns, 3 turns, and after will damp away. Normal, okay, you lost your energy. Also you say, okay, I force it, but I force it with a non-resonance period. You see, I put energy this, here, so I miss my solitary wave. So the wave will not take the energy that I wanted to give. But of course, you can imagine if you have the right period, it is here, you can keep your solitary wave forever like that. So in fact, we came back to the lab, and before the scientist that I am became an artist, you know, when I did the cusp, for instance. But here it is the artist who came with me to the lab, and we made these measurements. This is the age of a wave as a function of the period of the forcing, okay? So we start at a very low forcing here. This is a period, very low in frequency. After a certain time, oh, the wave appears. We continue to increase the period, it goes there. And after we decrease the period, it goes there. And after, back here again, okay? So here it is clear what we have. In fact, we know it is a resonant phenomena. So what we have is a curve, a solution is something like that, okay? It is something like that. It's a nonlinear resonance. We know what is a resonance, you know. But if it is nonlinear, it can be tilted. So what happens if we are in this regime here is we have 2 solutions. One solution is I have a big wave with a big amplitude, and the other solution is I have no waves. So if we are too close of this position here, and of course when you are in the museum you wanted to have the highest wave as possible to make a big effect. But the danger is maybe if there is a small perturbation, if there is a evaporation of water, so the velocity of the wave changes a bit and so on, you can lose it. Okay? So this is the lesson that we took from this piece of art, okay, in science. So we discover a nonlinear resonance on this phenomena. And that was in fact my last slide. So I thank you very much. I hope I was not too long on that. That was a pleasure to talk to you anyway. Okay, thank you.
Question? Preguntas? Sergio?
The phenomenon that the frequency goes to infinity in a finite time.
Yeah.
I see something like that with the radicalized solution that
Of a bubble? The bubble that oscillates?
the oscillate goes constant.
Okay, maybe, I don't know. Maybe it's possible.
Similar.
I don't know this. I know the Rayleigh-Plesset equation. I know that the bubbles obey that, but I don't know if the solution.
Because
The period is going to zero.
I think it's similar
So it's similar to a ping pong ball. So you should look at it. I don't know, but that's a good idea. Yes. Yeah. Yes, certainly there are many phenomena in real life, I would say, that obeys this thing. What I prefer the most is what I said before. Yes, it is this obeys the singular behavior, okay, and I stop it. But so the singular time does not exist. But before it was obeying the rule. And I think this is quite neat, yes.
This on the torus.
Yeah, it's a torus.
It's very difficult to make.
What is difficult is not difficult to make. Maybe I work 3 months in the lab to have all the parameters correct. What is difficult is to have something beautiful, no defects. You see what I mean? Something you can put in a museum, you can present to the public. You cannot have a screw there. You say you want to have something neat, and this is the most difficult part. As scientists, we don't care about that. Yes? You put a screw there, and you see the screw. What's it? There, no, you must not see nothing. There is a mirror all around here inside. You see, it's a sloped bottom. Okay, the bottom is like that because the circle, the outside circle is larger than the inside. Okay, so you need the wave to go faster and on this wall, but faster here. So the depth has to be larger here. Okay, so you have to calculate the shape here and so on. But this is easy algebra. Okay, but this is a mirror here. So and you don't want to scratch on it, or everything is destroyed. So you have to work very carefully, and this is. Yes.
So this cup that you put light.
Yeah.
Can I do it in my home?
Yeah. Yeah, of course. Yeah. This is exactly that. This one there, what was it? Yes, this one. This one, I think, Michael Berry, you know his name maybe? Michael Berry is a very famous English professor, and he worked a lot on the cusp on singular behaviors. And in fact, I think in one of his papers, he has these photos where he studied the cusp where you have different colors, different wavelengths in the light. Okay, you see there is a blue and a green and things. And he said that this photo, to make this photo, he used one tile, one ceramic, something like that, in his bathroom. You see, so it was home. Yeah. I think it's color glass or something like that. That's it. But you're right, behind a cup of wine or glass of water, you see, we have cusp everywhere. Yeah. Caustics is coming from the name caustics is because it is chaud. What is the Spanish is called? C'est quoi le mot espagnol pour chaud?
Caliente.
Caliente. So caliente is the same as caustics. Caustics is because it is hot. Caustic like chaud or caliente. The word is that because we know that with a lens we can put fire. Yes. So it's a hot point.
¿Alguna pregunta más?
Okay.
Well,
Thank you very much. Merci.